We present a client-server streaming terrain rendering system to serve and stream large terrains to heterogeneous clients. The process is sensitive to both the client's capabilities and network bandwidth. Streaming allows us to have dynamic virtual worlds in which multiple users could collaborate at the same time. The basic requirement of a geometry streaming system is to achieve user experience akin to local rendering. A single server serves multiple clients of different profiles using the same content repository. This repository could change with time. New content may be added or removed at will. The typical requirements of a streaming system are to achieve interactive frame rates, high quality rendering, and immunity from changes in latency. We utilize a combination of levels of detail, client size visibility culling, server size visibility detection, speculative prefetching with caching, as well as geometry compression techniques. The system ensures minimum server response time. Terrains can easily be divided into tiles, which may be efficiently compressed using standard image compression techniques. They may be tessellated at the client end into the final rendered mesh. We may individually stream these tiles depending upon need. The server sends a collection of tiles to the client depending upon the potential visible regions of the terrain based upon viewer position. We aggressively utilize level of detail to reduce the amount of data to be transmitted to the client. The utilized bandwidth between the server and the client is monitored at regular intervals to select the optimal representation to be transferred. For sending a higher level of detail, we only need to transmit the difference between the super sample lower level tile and the actual tile. The residue is compressed using the extremely efficient PTC image codec. Using multiple levels of detail also allows us to have a higher level of performance at the client end. To reduce the amount of data to be transmitted and also to avoid effects of changing latency, we prefetch sections of the environment that might potentially come into view in the near future. We use motion prediction to estimate the position of the viewer and then request the sections of the environment in advance. We use a least potentially visible caching scheme that expunges tiles from the cache based upon their potential visibility, considering the current direction of motion, which allows significant reduction of transmitted data. Dynamic objects can be introduced into the virtual environment. The server must continuously monitor the state of all dynamic entities. We use a method of lazy updation for dynamic objects where the client only downloads the model when it is actually visible in its viewing frustum. Any change to the environment by the client is immediately notified to the server, which then relays the information to all connected clients. Other clients may then download change objects at will. Our system allows us to incorporate user-defined annotations to the terrain. These annotations are sent to the server immediately after being added. The server updates its terrain database accordingly. Such techniques are especially useful for community-based mapping applications. We presented the design and implementation of a terrain streaming server. A terrain streaming system such as this would be extremely useful in collaborative 3D mapping applications, massive multiplayer games with completely dynamic environments, and also for serving low memory footprint devices such as PDAs.